MapReduce is a common pattern of querying data where we take a bunch of records and perform some operation against all the records which transform them into key value pairs. Then, the results are shuffled into more useful orders for reducing and they are reduced down into a single value. This is a common pattern where we can implement ourselves. The concept of MapReduce often comes as out-of-the-box solution in things like Hadoop or Mongo, as it's great for paring down a lot of records across huge datasets. In particular, this often occurs in some distributed file system across a cluster, and we perform map function against each node in the cluster.
Today, I will explain how to analyze a parallel algorithm using word and spine. Definition. Word, referred to as T1, is the total number of operations or steps if a single processor does everything, while spine is the longest chain of steps that must run one after another due to data dependency. It tells us the shortest time needed, even with unlimited processor. So, both word and spine are important to measure a parallel algorithm efficiency. Second, example using MapReduce. If our input have 4 files, file 1 apple banana, file 2 apple apple, file 3 banana banana, and file 4 banana apple. So, let's calculate the total operation. Map phase. Each file has 2 words, so 4 files multiple 2 equal to 8 map operation. Second, shuffle phase. We group all 8 key value pairs by key equal to 8 operation. And step 3 is reduce phase. Apple appears 4 times. So, to reduce 4 values, we need 3 addition. For example, 1 plus 1 equal to 2, 2 plus 1 equal to 3, and 3 plus 1 equal to 4. Same for banana. So, banana also got another 3 addition. So, total reduce operation is 6. So, word equal to 8 plus 8 plus 6 equal to 22 operation. Now, let's find the critical path, which is spine. For the map phase, all files run in parallel, which is 1 step. For the shuffle phase, we grouping, so it will be also 1 step. And the last step, which is the reduce phase, the longest chain is 3 addition for either apple or banana, equals to 3 addition. So, spine equal to 1 plus 1 plus 3, be 5 step. Parallelism, we use word divide by spine. So, 22 divided by 5, we got 4.4. This means the algorithm can run 4.4 times faster with multiple processors than just one. To summarize, word and spine help us measure how efficient a parallel algorithm is. By calculating total word and the critical path, we can understand how much speed up we gain with parallel processing. This is important to design faster and more efficient system.
Next up is Amdahl's law in MapReduce. Amdahl's law formula is defined as 1 over 1 minus p plus p over n. The 1 minus p is the serial portion and the p is the parallel portion, and n is the number of processes. Relating to our algorithm, which is MapReduce, the map phase is the serial phase because the data was split into chunks and then processed independently and in parallel. This phase is partially parallel, but due to its heavy communication and synchronization, it can be considered as the serial portion and have overheads in the shuffle sort before it starts the reduce. Why we can have unlimited speed up? In Amdahl's law, it shows that the speed up of a program is limited by the part that cannot be parallelized. Even if we use more processors, the serial portion becomes the bottleneck that stops us from getting the unlimited speed up. The example of the bottleneck such as heavy communications, grouping, and also synchronization. From the analysis of MapReduce in the previous part, we have the information of the total work, which is 22 operations, and each span has 5 steps. Since no number of processors is mentioned, so let's say we have 3 processors. First, we need to estimate the serial fraction dividing the span with total work to know the total work that cannot be parallelized. So the serial fraction is 5 over 22, which is estimated to be 0.227. And then we find the parallel fraction, which is 1 minus serial fraction, that is 0.227. And we got around 0.773. Now we have all the information to plug it inside the Amdahl's law. Then we got the equation is 1 over 0.227, that is the serial fraction, plus 0.773, the parallel fraction, over the 3, the number of processes. And the answer is estimated to be 2.063.